So in this video, we're going to begin to explore exponential functions in this new series, nonlinear relationships. Now, in our exponential functions, these we have touched on before, but we'll go over them again in this video. Basically, all these functions, there are a certain family of functions that have x as the power of a constant. So for example, 3 to the power of x. And these are defined by a general rule, y equals a to the power of x, or y equals a to the power of negative x, where the constant a is greater than 0. Now, these graphs are shown below. Something like the first one, in the case where a is greater than 1, this is an example of what we call exponential growth. Now, anytime we say the word exponential, it means at a faster and faster rate. So if you say something gets exponentially bigger, it means it gets bigger and bigger, quicker and quicker. If you talk about exponential decay, which is this case where something goes down, this is where the rate decreases. So the number goes down. So the direction of the graphs reflects this. Exponential growth, if you look from left to right, our graph is getting bigger and bigger, quicker and quicker. Our exponential decay starts high and then it goes down. When something decays, it goes down. Now, many of our practical uses for exponential functions, which we will be doing mainly in this topic, have a being greater than 1. Now, this is your typical sort of exponential, which we will look at in just a moment. Now, in this video, I thought I'd go over just a couple of key features of these exponential graphs and show you some of these on Desmos. So basically, going through these dot points, the graph lies wholly above the x-axis because a to the power of x is always positive, regardless of what value x is. So if you imagine your graph, even this one, when a is greater than 1, it's always above the x-axis. Now imagine a table of values. Let's say this was the graph y equals 2 to the power of x. As your x values go up, let's say 2 to the power of 1, that gives you 2. 2 to the power of 2 gives you 4. 2 to the power of 3 gives you 8. It's always going to be above the x-axis. Now, specifically when I have 2 to the power of 0, anything I have to the power of 0 equals 1. We learned that back in indices. So this second dot point, because something to the power of 0 always equals 1, graphs in this form that I've written up here will always pass through the point 0, 1. So this will always be the y-intercept of these graphs. Now, quickly going back to this idea of why it's impossible for the y values to be 0 or negative, I'm going to show you an example of this on Desmos. Now let's consider that graph that we talked about. This is y equals 2 to the power of x. It keeps going down to 1.9, one moment. Okay, so if I zoom in, right, you can see all these key points we sort of talked about. So when x is 1, y is 2, when x is 2, y is 4, and it's going to keep going up at a faster and faster rate. You can see it get really steep as you go up here. But let's look what happens on this section, because we have to recall that if my power was negative, for example, I had y equals 2 to the power of negative 1, negative powers are going to make indices that are fractions. We talked about this reciprocal relationship where, going back to our notes, if I have, for example, y equals 2 to the power of negative 1, that can be written as 1 over 2 to the power of 1, or 1/2. If we had y equals 2 to the power of negative 2, using negative indices, it gives us 1 over 2 to the power of 2, which gives you 1 over 4. So your fraction, as your power gets smaller, so it goes to -3, -4, etc. in the negatives, our fraction is going to get smaller and smaller and smaller. Let's actually investigate that. We can pretty clearly see here when x is -1, y is 1/2. As we go down to 2, y becomes 1/4. And as we keep going down, we're going to get an 1/8 here, and it's going to keep going down. Now, our denominator on our fraction is going to get bigger and bigger and bigger, which means that our fraction is going to get smaller and smaller and smaller. So it's going to get really, 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 really close to 0. But if I continue zooming in, you can see it will never actually touch the x-axis. It will get really, really close to it. So we say, you have a special name for this, that the x-axis is an asymptote. So it's a line that the curve approaches by getting closer and closer, but it never reaches it, okay? And this is because of this idea. Our denominator is going to get bigger, but we're never actually going to reach 0. We're going to approach 0. As we get to 1 over 1,000 or 1 over 10,000, 1 over 1,000,000, it's going to get so close, but it will never actually get to 0. Now, we have a couple of kind of transformations we can make to these graphs. So the graph of a to the power of negative x is a reflection of the graph about the y-axis. So this is an example of it up here. Our graph goes from doing this to basically being a mirror reflection. Imagine we flipped this around in the horizontal direction and we reflected it around the y-axis. It would look like this. Let me actually show you this on Desmos again. If, say, I put let's go back to our graph. If I put a negative in front of this x, you will see my graph flips. So it still maintains its same shape and steepness, but it just flips around. Here we have it regularly. We put a negative, it now becomes a decay graph. So this is how we can start to work with these reflections with the negatives. Now, this base number a, here it's 2, for example, we use that in our graph. As this number gets bigger, or changing the value of a, for example, something like this, will affect the steepness of the graph. So the y values will increase at a greater rate when the x values increase, the bigger this base number a is. And I'll show you this on the graph. Now here we have a to the power of 2. We have 2 being a, so 2 to the power of x. As this gets bigger, my graph gets steeper. So it will get higher quicker. We can see it's really, really steep here. As we go down, it gets less steep. And adjusting this always adjusts the steepness of the graph. Now, last thing is we refer to the growth function as we talked about when a is the power of a is just x. There's no negative in front of it. That is a growth function. When it's negative, it is a decay function. One last thing I'll quickly show you. As I cycle through these numbers, as I get closer and closer down here, you'll notice the graph gets pretty flat. Because we said we look at these graphs when a is greater than 1. The reason why it's greater than 1 is because something weird happens when we get to a equaling 1. We actually see a straight line. This is just a horizontal line passing through 1 in the y. So this is essentially the graph of y equals 1. The reason why this is that if your base number is 1, any number you raise 1 to, any power that you raise 1 to, so 1 to the power of 1, 1 squared, 1 cubed, 1 to the power of 10, it's always just going to give you 1 back because 1 squared is just 1 times 1, which gives you 1 back. 1 cubed is 1 times 1 times 1, which gives you 1 back. So at this point where the base number is 1, this ceases to actually be an exponential graph. It just becomes a linear graph. So that's why we're just dealing with the values of a being greater than 1. This is where we really see this exponential curve kind of shining through. But that's just us introducing the exponential function. We'll go through graphing that in the next video. But thank you so much for joining me, and I'll see you next time.